Okay, for dearest friends at home, I will do the warm-up with you. Everyone else in here is doing it on their own because they're here. Okay, so it says let A and B be independent events such that the probability of A is 0.3 and the probability of B is 0.8. Find the probability of A and B. What do you guys know about independent events? The probability of A and B is equal to? Okay. So, did they just give us all that stuff? They sure did. All right, folks, what did you get? Yay. Okay. Next, find the probability of A or B. You're going to use the formula, right? Okay. So this guy is going to be A, which was 0.3, oops, plus 0.8 minus 0.24. And what did anybody in the, it's called you guys the audience. What did anybody in the audience get? Good job. Very well done. Are A and B mutually exclusive? Justify your answer. Can anybody tell me the formula that we would use to prove mutually exclusive?
Probability of A or B equals probability of A plus probability of B.
Good, and you're trying to prove it. So let's put a little question mark there. Are they equal? And then we can check it out, right? The probability of A or B was just found above, and it is in fact 0.86. And we're going to see if that is equal to the probability of A plus the probability of B. Still checking, right? Okay, so 0.86 is equal to 1.1. No. You would put a cross over there. Therefore, I meant to write A and B are not mutually exclusive. Sometimes up here it'll say justify, explain. If you do it this way every time, you kind of encompass all of it, so you don't have to worry about what the command term was and did you show enough work. And, you've demonstrated both mathematically and with your words that they are not mutually exclusive. Now you don't need to get bogged down by the words, okay? All right. Today we're doing probability trees. So the last couple of days have been a little dry, I know. But now we get into probability trees and they're fun because they model real life systems and we can use them to figure out cool stuff. So let's look at this cool example at the bottom of the page. It says, Dumisani is a student at IB World College. The probability that he will be woken up by his alarm clock is 7/8. I'm just going to jump down here really quick because it helps to fill out the diagram as we go through. W is the event that Dumisani is woken up by his alarm clock. So let's go to the tree, and it looks like that is the event that's happening first. He is either being woken up or not being woken up by his alarm clock. So the probability that he is woken up by his alarm clock, or W, is 7/8. We know that branches on a probability tree, this one and this one are going to add up to 1, so this guy has to be 1/8 for the probability that he is not woken up by his alarm clock. Okay, first clue, done. If he is woken up by his alarm clock, think about what that if means, right? That if means that we are tracing along this specific branch, right? If he is woken up by his alarm clock, this is kind of getting into the territory of a given, right? If this happens first, now we are examining the probability that he will be late for school. Okay, so the probability that they are giving up to us right now, that 1/4 is going to go on this line right here. Do you see how that kind of works? The audience is really quiet today. All right, that one is done. Now, if he is not woken up by his alarm clock, which branch are we tracing across? Whoop, not woken up, right? He will be late for school. So now we're filling in that probability here, right? It's saying if this happened first, now this is the probability that he will be late for school, which is 3/5. Okay, so let's fill out or complete the tree diagram to the right. Okay, so this guy's going to be 2/5 and this guy's going to be 3/4. Can anyone tell me what the second event was? If the first event was being woken up by his alarm clock, the second event was being late for school. So do you see when a tree diagram would be appropriate? When we have one thing happening first, and then depending on what happened first, we get into the second part of the branches, which is the second event. Okay? So now we go to B. It says calculate the probability that Dumisani will be late for school. So what you're trying to find is all the different ways that he can be late. So all the different branches that terminate in an L. Those will be all the ways that he ends up being late for school, right? And it looks like there's how many ways that he could be late for school? 2, right? So we multiply across branches. I would write yourself a big little note here. Multiply across branches and then add different branches. And think about what that means, right? When you add 2 different things, that's the OR. Did you hear that in A2 last year, right? The adding is the OR, right? It could happen this way. He could be woken up by his alarm clock and late, or he could be not woken up by his alarm clock and still late. That's how you would add the 2 different branches together, right? And then notice the and is going across the branches, right? W and L, that's going to be multiplication. Not woken up by his alarm clock and still late, that's going to be multiplication across those branches, okay? So and is times, or is add. Okay. So we're trying to find all the ways that he's going to be late for school. So you're going to multiply across the branches, right? Sorry, I'm going to zoom out here so I can see everything. So the probability that Dumisani will be late for school can be found by multiplying across the W and L branch, or multiplying across the not W and L branch. Those are the 2 ways he can end up being late, okay? So go ahead and type this in your calculator and let me know what you guys get for the probability that he's late for school. What'd you get? You don't like the fraction?
47/160.
I'm upset you don't like it because it's right. Good job. A fraction only a mother could love, but it's still the answer, right? So the probability that he is late is this thing. Make sure you label it because you might need it later on, aka in part C. So given that Dumisani is late for school, get in the habit of, given that you write your slash on the paper, given that Dumisani is late for school, what is the probability that he was woken up by his alarm clock? Okay, Damien told me that he requested to sing the song this time, so go ahead, Damien, take it away. I don't think I did. I'll sing with you. Given goes down, below, and is on top. That given it haunts me. Oh, that was good. Conditional probability. All right, so remember the and comes from multiplying across branches. So let's go find that branch where it's W and L. Oh, it's right up here. It's this guy. So we have 7/8 times 1/4. That's going to be my numerator. 7/8 times 1/4. And then the probability that he's late is going to go down, below. Go ahead and type it in. What do you get? What'd you get?
35 out of 47.
Can confirm. Anybody else get 35 out of 47? Yes. Okay, so let's put our statement all right here at the end. So given that he was late for school, the probability that he was woken up by his alarm clock is 35 out of 47. Okay. Let's look at question 1. It says J and K are independent events. Given that the probability of J, given that K happened, is 0.3. Wait, stop. 1 second, right? Probability of J given that K already happened. So if it just tells me right there that J and K are independent events, does it matter that K already happened? So what is the probability of J given that K already happened? Probability of J. Okay. Well, it's not a J. K. Give it, okay, and that is equal to 0.3. Okay. And the probability of K is equal to 0.5. Find the probability of J. Oh, dang. If you knew a lot about independent events, you don't even have to do anything. That's the answer. Yay. Okay. So, good on you. Okay. Does anyone need further explanation on this one? No, it's just you being a little hacker. You're always the hacker, right? Okay. Question 2. Is anyone in here a hacker? Don't worry, this isn't being recorded. It's being recorded. You all looked at Jacob. Are you? No. No. Is computer science a passion of yours? Ah, I see. Cool. Okay. Question 2. In any given season, a soccer team plays 65% of their games at home. Okay, you're reading all these little stats here and you're trying to isolate what is the first event and what is the second event because that will help you set up your tree. Okay, so let's keep reading. When the team plays at home, they win 83% of their games. When they play away from home, they win 26% of their games. What is the first event? Whether the team is home or away, right? So let's call it home or not home. Okay, so any given season, a soccer team plays 65% of their games at home. So that means we're going to put 0.65 on that. I prefer to work in fractions or decimals just because it makes it easier to multiply. If you put percentages on there, it's kind of like, right? Okay, so if that is the percentage that they're at home, what's the percentage that their games are away? Or the percentage of their games that are away? Nice. Okay, so that was the first event. What's the second event? Given that they are home, whether they win or lose, right? Okay, win. Not win. Win. Not win. Okay. So now let's try to put these clues on here. All right, first one's done. When the team plays at home, so which branch are you supposed to be on? We're on this branch, right? When the team plays at home, they win 83% of their games. Okay. So that's going to give me 0.17 down here. Okay. When they play away from home, so now we are on this branch. When they are away from home, they win 26% of their games. Okay. So then what's the other thing down here then? Right? Okay. So now, hello. Okay, so now what are we supposed to do here? Let's see. Find the probability that the team wins the game. Okay, does anyone feel comfortable, like, explaining what we're looking for here? Where are all the times that we end in a W? Find the little tendrils or dendrites or branches that terminate in a W, right? Okay, so we have this and this. Is that what you were going to say?
Yeah.
Exactly what she said.
Exactly what you were going to say. Yeah.
Dendrites and all.
That's what they're called, right? Yeah.
Yeah, and then they're
Phalanges are on a hand.
yeah.
Okay.
Well,
Right?
they're
Yeah.
either your toes or your hand.
Oh,
Or your fingers.
really?
I don't know the difference.
Yes. Okay, good to know. Okay, so what do we do? Somebody
Multiply that.
multiply across and then add different branches. Okay, cool. Let me know what you get when you do this. I'd prefer a decimal because I think the fraction would be sad. 0.6305. That's what I got. Anybody else get that?
Yeah.
Boom. Okay, so we're supposed to round our answers to 3 significant figures, but for further working, we're going to use that version. So just so I can keep track of it, I usually do the little like rounded symbol, and that's my 3 sig figs answer. And then I just know that I'm going to be using the other one when I keep going with stuff. Okay. So, oh, yes, emails. If the team does not win the game, ooh. We've traced along a branch, haven't we? The team does not win the game. If the team does not win the game, find the probability that the game was played at home. Okay, so we're supposed to be in a special portion of the tree. Take a second and try to figure out. Write down your given statement and think about what you think it's going to be, okay? Okay, so if the team does not win the game, find the probability that the game was played at home. Is that what you wrote down? Yes! Okay, so Dylan is going to sing for us now because he was requesting as well. Given goes down below and is on top. That was beautiful.
I appreciate it.
Are you a music guy?
Kind of, yeah.
Yeah, we're learning so much about each other. We have a computer representative. We have a music representative. You know the difference between phalanges and dendrites. All right, where are we going to find H and not W? It's this. Right, it's getting a little obvious. That's good.
That's the one one that's not
H.
H.
Ah!
It's
Ah!
so obvious.
It's so, it is so obvious. H and not W. There we go. So you got 0.65 times 0.7. Quietly erases. 0.65 and 0.7. Over, ooh, work smart, not hard.
1 minus 2.6.
Yes. So we could go to all the branches that terminate in a not W and add them together after we've multiplied across. Or we could just recognize that the probability of W is right up here, and we could do 1 minus that bad boy, and we could get our denominator in quite a less time. Go ahead and type that in and let me know what you guys get. That, people at home, that was a heavy sigh.
0.29905.
Oh man, my answer was 221 over 739. Let's see if they're equal.
What did you get?
Oh no, this is a preview of coming attractions. Don't look. Oh my gosh. Okay, guys, I'm stressed out. The TAP app, which is how we like activate a lockdown, looks very close to my calculator, like icon. Okay, you got this. All right, so I got 221 over 739. Hi. What did you guys get?
Yeah.
That? Yay! Okay, cool. Okay. Perfect. All right. I think we're going to do one. We're going to skip 3. You're going to go back and do 3 independently, but it's like review and stuff we already did. Not saying it's not important, but I wanted to keep working on writing trees, okay? Let's go to 4. We're going to make some more trees. We are reading for the first event and then the second event. Go ahead and read 4. I want you to tell me what the first event is, then what the second event is. raise your hand when you think you have the first one. Yes.
Which drawer?
Okay, and then how many drawers are there? Right, you walk up to the dresser. How many drawers are there? Okay, it's equally likely that you could pick drawer 1, drawer 2, or drawer 3. What's the probability if it's equally likely and there's 3 things? 1/3, 1/3, and 1/3. Yes! What is the second event? Anybody else? What's the second event? Gold coin, or what else? A silver coin. Good job. Okay, drawer 1 contains 3 gold coins. And okay, no silver. Drawer 2 contains 2 gold coins and 1 silver coin. Drawer 3 contains 1 gold coin, 2 silver coins. Okay. A drawer is chosen at random, and from it a coin is chosen at random. Find the probability that the chosen coin is gold. All right, let's find all the branches that terminate in a G, multiply across, then add them together. For people at home, we are being interrupted by several human bodies entering the class. No, I'm just kidding. Hi, guys.
Well, so quiet.
How was your field trip?
It was really good. Right, Declan?
Cool.
I overslept.
Oh, well, that's why you were sick. You overslept. Natalie said that.
Oh.
So are you both?
Yeah.
So you overslept because you're sick?
Yeah.
Oh, I thought you were saying like, oh, I'm sick. I overslept.
Yeah.
I'm sick. You could have done it in your calculator too. Sometimes it's just easier to just do it in your head. But did you guys get 2/3?
It was so quiet and cozy in here before we entered.
It is.
Like we disrupted.
We learned so much about each other too. It's beautiful.
I hope we didn't learn too much math while I was gone.
Not a great day to miss, but it's okay. We have it recorded.
Wait, what page are we on?
21.
My pages don't line up with yours. 21, yeah, I think.
Oh, yeah.
Okay, so given that, somebody set it up for us. Given that, the chosen coin is gold.
I looked like we had a face, bro.
Find the probability that drawer 3 was chosen. Adriana, do you want to sing for us? I'll sing with you.
Oh, I'll do it.
Given goes down below and is on top. That given it helps me.
Okay.
I love you, I'm sorry. No, that's not how it goes. Okay, so, that's a G. G. Okay, so now I'm trying to find the probability of D3 and G. I'm going to multiply across branches. D3 and G. So that's going to be 1/3 times 1/3 over the probability of G is gold, which is up here, 2/3. Okay, 1/9 divided by 2/3. See if you could just like practice, right? Can you do that by hand? Remember, Kentucky Chicken Fried. Keep, change, flip. Ooh, cross reduce. A little cross reduce for you. What is it? Oh. There you go. All right, cool. Oh, we're on page 21. I'm on a different page. Okay, I think you guys should cross off question 5 because it's a repeat. We did it the other day. And then you guys are going to do independently question 3, question 6,
Wait,
question 7.
6, 7?
What?
What was one before 6?
uh,
Where's 3?
So it's like 3, 6, 7. I want to show you 8. I feel like 8's pretty sneaky. And then you're going to do 9. And then you're going to get as far as you can in 10. But I want to show you something really cool on 10 because it's so cool. It's like a little a bridge between something you already learned and something that
Will you
is cool.
will you like post like the note? Well, they're already on there. Actually, never mind. I forgot.
This is being recorded. Yeah, you can watch this. Yeah. Okay, so since some of you just joined us, how about I walk you through 8?
Oh, it actually is being recorded.
Okay. Yeah.
Oh, I thought you were joking.
No.
Why is it being recorded? Is that if we're missing it? Is that why?
Yeah.
Oh, okay.
Yeah. So actually, I guess I could stop it now. Oh no, Alexis isn't here, right? Okay, Alexis, this is for you. Okay. So question 8 says, the events A and B are independent such that the probability of B is equal to 3 times the probability of A. So remember, they gave me the probability of B in terms of the probability of A. So I should write myself a little let statement where we have let the probability of A equal X. Because then now I have the probability of B is what? 3X. And I'm like, oh, okay. Meh. All right. Then they give me the probability of A or B is 0.68, and I have to find the probability of B. Seems like a lot going on. That's okay. I see an OR. I'm going to set up the OR formula because I feel like that's what's going to give me the most stuff going on here. So the probability of A or B will be the probability of A plus the probability of B minus the probability of A and B. All right. Let's see if we can fill in any of this stuff. I have the probability of A or B is 0.68. I have the probability of A is X. I have the probability of B is 3X. And then, the probability of A and B. Can anyone tell me where that could come from?
You probably would
Independence.
be independence.
You
Probability
what?
of A.
Independence.
They're independent, so this is the same thing as the probability of A times the probability of B, right?
Yeah.
Yeah. Right, so this is what it's rooted in. Definition of independent events. So B is 3x times x. So I should get 3x squared. Yes. Okay, it's giving quadratic. It's giving disgusting. I think I should graph it because it's disgusting. Does that sound good?
Yes.
Okay. Let's get this in standard form set equal to 0 so we can just graph it and find it. What graphical feature are we looking for? Mountains. No. What are we looking for? Let's get it in standard form set equal to 0 and then you can talk to me, okay? Let's see.
Oh, we're looking for the zeros. So the
Yeah.
intersections, the x-intercept.
Yeah.
Interceptions.
Interception. So what you're going to want to do then is be like, okay, I'm graphing this for x-intercepts. Look how rough the sketch can be. You just are like telling whoever is grading your paper how you found your answer, okay? Now, I'm going to say this once, and then I'm probably going to say it again. But when you're using quadratics to figure out a probability, think about what the two solutions are. They're tiny little decimals, right? So if you ever think it just hits once, you should zoom in and make sure you didn't miss one of the other solutions, okay? This happens all the time. Like one of them is 0.3 and one of them is 0.4. You can't see that with your eye, so make sure that you either use graph trace to make sure you don't miss one. Does everyone know how to do graph trace? So that way you're like, okay, that's the first one, and then that's the second one to make sure you don't miss it. Because if you just scan, you might like be like, oh, it just touches once. Does that make sense? Can everyone give me a thumbs up that you will remember to go in and look for the two solutions because they're tiny? People who didn't give me a thumbs up, I cannot help you. Okay, so I've got two options here. I've got 0.2, and then I have 1.133. Who can tell me what is the answer? How did you know 0.2 was the answer?
Probability can't be one.
You can just write reject, meaning like
I think it's a failure.
it is an abject failure. And then we are taking 0.2. But what is x? X is the probability of A, right? What did the question ask us to find? So the probability of B is just 3 of those. No, I would not like to edit my calendar, but thanks for asking. 0.6. Okay. All right. I would like for you guys to peel off and try to do some of these independently. And then for the people that just showed up, I'll do one with you so you're not totally lost. But if you were here, try to do it on your own, okay? Let's do the seeds. Okay. Question 7.
Who's banana dog?
He was a member of our learning community a few years ago and he passed away. Someone dropped him in the bathroom and his face came off.
For like the IA task, you put your name as banana dog.
Oh, yeah.
So I was like, what is like that?
He wrote that before he met his untimely demise. So we have a packet of seeds contains 40% red seeds and 60% yellow seeds. Hey, you should put the 60% yellow seeds on the diagram, and that'll go right here. Why? Because branches add up to 1, right? It has to be one or the other. The probability that a red seed grows, I've traced across the branch, and now I'm filling out the second part up there on the red branch, okay? So the probability that a red seed grows, think about what that means. The probability that a red seed grows. Probability of red and grows. Yeah? You see what it's kind of doing? And that a yellow seed grows is 0.8. Yellow seed grows. So what's going to go in that little grows line right there? Excuse me. They just gave it to us, right? If this was red seed grows, yellow seed grows would be this line right here. Okay? So we're on the yellow branch and we're putting in the probability that he grows. That's going to be 0.8. So now I can fill out the rest of this whole thing by just knowing my probability relationships. And I'm cooking. Here we go. BI. Calculate the probability that the chosen seed is red and grows. So you're tracing across the branch to kind of find probability of red and grows. When you trace across a branch, you multiply. Red and grows would be 0.4 times 0.9. All right, what'd you guys get for red and grows? Get that count. 0.36. Next, calculate the probability that the chosen seed grows.
In general.
Yeah, right? So we're going to look for the chosen seed means it could be yellow or red. We're basically just looking for all the branches that terminate in a grow, right? So what we do is we multiply across branches for the and, then we add different branches for the or, right? It's saying that you could have a seed that grows this way, or you could have a seed that grows this way. Therefore, you would multiply across branches, and then, that's not what I'm saying. Multiply across branches and then add the two different branches that you've multiplied across. Does that make sense? This is the and, this is the or. Okay, so calculate the probability that the chosen seed grows. Probability of grows. is equal to, well, we know redden grows, that's 0.36, but let's just set it up. So if you were looking at this later, you could figure it out. And then 0.6 times 0.8. Tell me what you guys get for the probability of grows.
And just like the answer,
Mhm.
oh, 0.84.
Mm-hmm. All right. Now, given that the seed grows. Audrey, did you want to sing this with us this time? Given that the seed grows, calculate the probability that it is red. All right, Audrey, I'll kick it off for you, okay? Given goes down, below, and is on top. Yes! Okay, so redden grows. We already found it. Hey. Grows. We already found it. Hey. Put in your calculator. What'd you get?
Who's got their calculator out? What? Oh. Well, I wasn't asking you. What do you need to?
Oh no, hurry up, my beard is growing. It's 0.36 divided by 0.84.
0.428.
Oh, is that what I get? Yeah. Nice job.
I was really calculator.
Okay. Very good. Thank you.
Yay.
Okay, guys, I think you can do the rest, and then I'm going to see you back in a couple of minutes for 10. People who are at home, I don't know, skip this part. I'll be around. Please stop me if you need help.
You said my problems 3, 6, 7.
You just wanted to say 6, 7.
I don't know, I
Yes.
just was
3, 6, 7.
And
Well, we
that.
just did 7. So 3, 6, 3, 6, 9. Yeah, and then you're gonna do 10.
Did you guys do 1 and 2 really? Sure then. Oh, you did.
Go back and watch the video for those. I just tried to do right. I can help you get started on them. Focus on the trees and some kind of birds. So go to. Try this. I don't think you need it. Okay, so first thing is select an area. Oh, you want yourself to be. Yeah. You're gonna need to. But if not, no, there's one of those, the rest are trees. Okay. So, this one going in a tree, we say, let's not do that one, let's do this. Okay, people who are on the field trip, we're doing 9. Anyone's not 9 in your loss or you're going, okay? Okay?
Yes.
Wait, oh wait, no, the homework is like finishing. Oh, that's not bad. No. So the following probabilities are down for 2 benchmark tests. Probability of cost. That looks like that's the first event. You can be R or not R. If R is 1/3, what is that? Perfect. Now the probability of S, given that R has already happened. Given that R has already happened, means we trace along the branch for R, and then we go to S. Does that make sense? Wait, no, he's right, 2/3 can't, I just say what? Oh, okay. I was supposed to. There you go. So like that, yeah. they're independent, they have a special relationship where the probability of the and is the two multiply.
Okay.
But don't, that's like the number one, gatekeeper of this topic, I would say, is like they overthink it and they're like, well, it's tired, it's not, you know what I mean, just find them in the tree branches, multiply across, add them together, and soon you start to get the half this and half.
Sounds like one, two.
And then what about probability of S? So you can find all the branches that terminate in S. So multiply across, and then add two given branches together. I circle across, so remember for all the branches that come from S.
Oh, wait,
That's
wait,
one of
wait.
them, that's the other one.
Wait, that's that one.
Is it? Oh my gosh, it's so small.
Is that what we right here with the X one, X one? So it's like, so it's like 415 circles.
Hold on, you add two different branches, yeah, because it's one way or the other, or is it?
Keep going. What's the This is the first time I've like run through it. I love the tree, it's cool, like that. Probably because I've learned it before, so it kind of helps out.
I love this, I already know.
I know, dude. That's the criteria for liking something. So
I already know. Yeah. So, given that has to happen, so you can send that for.
Oh, so it's that.
Does anyone else realize with the baggy pants trend that you like want to wear? I've never been like a hands in my pockets person, and I with the baggy pants on and my hands in my pockets. You just say you're not very great, you're.
No, I'm just saying like very tight. Like,
These?
they're like medium.
They're a little too short. That's to be
I hate the
expected.
feeling of short pants. Oh my gosh.
That's my whole life, that's where I live.
It's just like Mr. Eden was wearing sweatpants at the train, and they were way too short for him. I like nothing like that.
I hate that shit.
So weird.
I'd rather have my pants drag.
2013, yes, you got it, do you understand it?
Yeah, that's
Boom.
valid. I would-
You understand it?
I
Boom.
don't know why.
You'd rather have like
Short,
two
I'm
tight
not
pants?
yeah.
I'm not.
I'm not here, but it looks like you're doing okay.
Well, I don't have to worry about pants being too short. I worry about the wrinkle being
Alright, so S given R, so it means we go to R, and we're tracing across that bridge.
Oh,
So that's good. So S given not R is not R, S, that's him, okay? Plus, like, if this was a test and you forgot which was which, this is given and it's on the diagram, so you would just say, oh, it's like on this branch. You know what I mean?
nice fall.
He was?
Really?
Mess. Big mess. Wait, oh, I can't, wait, do I have enough time for you? Yeah. Yeah. Why are you like? It's just way back.
I promise I know how to do problems like these. It's just like it's been like 5 days since I've done math because of like the long weekend. So how do I like is this stuff through like De Morgan's law or whatever?
This is three.
Three.
Oh, De Morgan's law is just figuring out the weird ones that are like the crazy knots.
Yeah.
That's not like a big thing that's being tested, right? So, consider the Athenian where the probability of the student not gives them 4, A or B is 7/8. Write down the probability of B. Well, if they gave you not B, I would just do 1 minus not B. You know,
Okay. Oh.
to get B.
So I thought that like what if there's like I thought like what if like there's something like that's not anything that's one like
That would be A or B not.
yeah.
A or B all of them
And wouldn't
is
that be
not.
wouldn't that be it's like one case like if you're subtracting went from 1 and you're getting 3/4, so like you're not accounting for this.
I feel like this is a great tool. Yeah. Split the desk over. I was lost too. This is a great tool to use if it's like crazy knots or if all this stuff you can just use the formula. Okay. So it's like this could be helpful, but it's like just use the formula.
Okay.
You know, because it can all be located on there.
Okay.
So then A and B.
Okay, so I know how to
So
do
now
this.
you have the
Yeah.
or, set it up, plug in everything in them, and now you're like,
Okay. I was
You
just
know?
confused on the first part.
No, that's like also the other thing. Conceptually, the things kids mess up is they don't know when to draw a Venn diagram,
Yeah.
and then, no. And then I forget what the other thing was.
It seems like such an easy question, and it's really throwing me for a loop.
Ooh, okay, so try to illustrate the sample space,
Because-
right?
So I got probability of L is 1/4.
Oh, are you asking about a different part? Sorry, I thought you were asking about the last part. Wait, so which part are you asking about?
No, the last part.
Yeah, okay. So, how many days are we examining? 3. How many times is he late on those 3 days?
Are you okay with that one?
1/4.
What is that?
Like, what do you?
The sniffles?
Like, that's what I got.
Okay, so you're like
Figure it out.
concerning yourself with the probability of him being late on a day?
Yeah.
But just think about, we have 3 days that he could be late. He's only late 1 time.
Okay.
So on the first day, he could be
Oh, I see what you mean.
late, but then the other 2, he must not be late, right? And then there's another chance where, or another representation where he's not late, not late, right? And then, or he's not late, late, right? So there's like 3 different outcomes. So try illustrating the
Oh,
sample
I
space,
see
you
what
know?
you mean. So like
Yes.
late, and then like late.
We can only be late 1 time, I think.
But can I do all of them and then see how many there are?
So you should do, he has to be late exactly once. So not late has to be the other 2. So he's late he is L1 and then not L for the other 2, you know? And then just cycle
I
through.
don't know. Like if I just, I don't know.
So like.
Like I get what you're saying, but
Yeah.
like I don't know how to
Just
write
do
it
it
down.
like systematically, right? Okay, so let's say he's late on the first day. Or he's, let's say he's late on the last day. It would look like that.
Yeah.
Now he's late in the middle, just because like I'm thinking spatially. Right? Now he's late on
Oh,
the first
okay,
day.
okay. So that's just
Okay, now think in that, get in that head space there.
Yeah, then goes down. Hey, give it a beat. Are you
Okay, are you guys ready for 10?
Down below.
This is so exciting. Wait till you see 10. So 10, let's go through the easy stuff at the top, right? So Adam travels to school by car or by bicycle. On any particular day, he is equally likely to travel by car or bicycle. The probability of being late for school is 1/6 if he travels by car. Look how they fill that out. Travels by car, probability of being late, 1/6. That's where it went. I'm on freeze. Sorry. Okay. The probability of being late for school is 1/3 if he travels by bicycle. Bicycle, late, 1/3. There you go. This information is represented by the following tree diagram. Find the value of P. Where is P? P is this. Oh, okay, it's the other side of 1/6. So what does P have to be? Good job. All right. Find the probability that Adam will travel by car and be late for school. Car and late. 1/2 times 1/6. 1/12. All right. Find the probability that Adam will be late for school. We're going to look for all the branches that terminate in a L, because being late is an L. So now we're going to multiply those all together. Multiply across, then add. So I have 1/6 times 1/2 plus 1/2 times 1/3. All right, so that'll give me 1/12 plus 1/6. Scale this up. probability of being late is 3/12. Or what would the reduced version of 3/12 be? Yeah. Okay. Given that Adam is late for school, find the probability that he traveled by car. Ooh, car and late. I found that. Probability of late. I found that. Car and late is 1/12 over 3/12. The probability of car, given that he's late, is 1/3. Okay. So far, so good. Are we all getting these kind of numbers here? I'm going through it really fast because I assumed you had a couple of minutes to figure it out. This is where we enter the dragon. Here we go. Adam will go to school 3 times next week, so that we're examining 3 days. We are illustrating a sample space for 3 days. Find the probability that Adam will be late exactly once. Okay, so this is late. This is not late. He can only be L one time. Let's put it at the first one. If he's late on the first day, he has to be not late the other 2 days. This is for 3 days, right? Other way it could happen. First day, he is not late. Middle days where he's late, then he's not late on the third day. Or he could be not late, and late, right? These are 3 different days. These are independent events you may multiply across for each time. What's the probability of being late? What was it? 1/4? Yeah? So then I could do 1/4 times 3/4 times 3/4. I could do 3/4 times 1/4 times 3/4. Do you see where I'm pulling these numbers from? 3/4 times 3/4 times 1/4. Now I would add for all 3 of these different ways that it could happen, and I would end up with 27 out of 64. So now I want you to stretch your brain, okay? You don't need to write this down. I'm just showing you a cool connection with something that we already learned. Could this not be rewritten as 1/4 times 3/4 squared? Can this also not be written as 1/4 times 3/4 squared? Could this also not be rewritten as 1/4 times 3/4 squared? Didn't we just rewrite all these in the same way like that? So couldn't you just take this and multiply it by the 3 different ways that it could happen? You could. Enter your favorite friend. What does this look like? What does that look like? N-crab. It looks like N-crab looks like binomial expansion. This is a binomial probability distribution. You don't need to know this yet, but I thought it was too cool not to share. So N is the number of trials. There were 3 days or 3 trials on which he could be P, which is the probability of being late, right? X is the number of successes or the number of times that he is late. He wants to be late exactly once. If I plug this into the N-crab formula, does this not reduce to 3, the 3 different ways it could happen, times 1/4 times 3/4 squared? It does. Blah! Oh my gosh, it's all connected. It goes all the way to the top.